Good morning or good afternoon to everybody. In this keynote lecture, I will address the topic of emergence of collective behavior in multi-species system, with particular focus as a case study on the microbiome, about its connectome, relationship with the environment, microbiome diversity, and diversity-related services. The microbiome is an incredibly interesting ecosystem whose diversity is extremely large, and we count more than 1,000 species for sure in our body, whose interconnection, whose connectome and the relationship with the environment is actually poorly understood, as well as how microbiome alteration is associated to health outcomes, a variety of different diseases. And yet, the microbiome is actually an entropic challenge, if you may want to say that. In reality, we should talk about holobiome rather than microbiome, because there is a deep association between humans and the environment, and yet the microbiome is truly associated with the environment we live in, and that actually complicates much more the complexity of the problem, and then it's a much bigger entropic challenge. It is also believed that the microbiome and human beings are actually in a perfect symbiosis, in a perfect alpha state, and that is actually associated to an optimal cooperation that maximizes biodiversity growth, and not the absolute value of diversity, as I will show later. The talk will see how health is actually imprinted into the dynamics of complex systems, complex human systems, but in general biological system, and I will make an analogy with the ocean systems. In particular, I will focus on the characterization of the dynamics of species, considering their abundance, abundance-based network inference and network topology, and macroecological diversity. These three distinct features of the microbiome are actually strongly interrelated to each other and associated to health states. More specifically, we will talk about collective information of species, and we will identify outgoing transfer entropy as a measure of node importance for describing topological transition associated to microbiome health state. And we'll show how that is actually related to the Kleiber's law that established the relationship between information processing as a metabolic flux and abundance as a body mass. Later on, we will make the association between network topologies with health states, and we will conclude by showing how the same transition can actually be mapped considering biodiversity criteria such as alpha, beta, and gamma. The foundational paper that are containing the material exposed in this lecture are primarily in my entropy paper, Optimal Microbiome Networks, Macroecology and Criticality, published in 2019, a Science Advances paper more focused on the methods to extract optimal information network, and the other side paper, I would say, but with the theoretical and conceptual relevance, such as one paper in Ecological Indicator with the title Towards Pluralistic and Conception of Resilience. I'm in a process of publishing a book about the critical values and ecosystem health, and that would cover a much broader topic, considering also large-scale ecosystem rather than just biological system in the area of medicine and public health. As for the microbiome, we're going to talk about a very common shift associated to a disease called inflammatory bowel disease. That is actually a relatively poorly understood illness related to an inflammation of the bowel, and that may be related to multiple causes. It can be an immune system malfunction or a food intoxication, in fact, or an infection. what is actually interesting is that the number of species in the gut is actually changing, and it's changing in a way that actually diversity of species is increasing, which is actually counterintuitive with respect to many misleading statements where biodiversity is actually increasing for an increased health condition. So it's a positive change. But we will show how actually this increase in species is associated to the generation of novel species from the current existing one, or to novel introduced species from the outside world related to the food infection. Now, an older statistical approach, for example, based on linear correlation coefficient, lead to poor pattern detection about the species interaction in the microbiome, as well as somehow species clustering, considering their dynamics. If we look into the raw data about the species abundance in the gut, we have a situation something like this, and this one is actually reflecting the data that we use in our study. Now, just making a clustering based on the probability distribution function of the species abundance that actually correspond to an entropic clustering. If we map how for example, the Shannon entropy changes over time, we're able to classify the species in 3 clusters. Unhealthy, that are actually the red one, healthy, the blue, and the transitory, that are the green one. We can also look into other population pattern, where the population is actually the set of species and abundance is the feature that we consider. We can see that there is a transition when we actually plot the exceedance probability distribution that is actually power law distributed, and the scaling exponent beta is actually related to the environmental fitness of the microbiome. Now, for the gut, what we actually observe in terms of Taylor's law that plotted the variance versus the mean of the abundance for all the species is that the unhealthy shows actually a greater variance with respect to the healthy state. And that is actually not what we observe for healthy, open, dissipative systems such as a large scale ecosystem. What is actually true is that if we plot the power law exponent of the exceedance distribution and the scaling slope of the Taylor's law, we identify a transition from healthy to unhealthy, where the transitory is, of course, in the middle. And then the alpha beta plot is actually a phase diagram that can allow us to identify fluctuation and microbiome transition, just based on population data of abundance. We can plot the same thing in another way. For instance, we report the variability in terms of variance that is actually proportional to the fluctuation related to the environment, and the fitness that is actually proportional to the environmental magnitude multiplied by a multiplicative noise, and this is actually proportional to the power law exponent of the abundance profile. We can actually identify this healthy and unhealthy state, as well as intermediate state that are actually not stable. Now, considering these 3 categories of health, these 3 categories of health are actually modifiable using some intervention. So, for example, if we are in the unhealthy state and we want to be healthy, we can take antibiotics. Prebiotics are actually guaranteeing the healthy state in a persistent way, and probiotics can actually help to push back and forth our gut microbiome from healthy to unhealthy. In parallel, in analogy actually, what we find for larger scale open dissipative systems, such as the ocean system, and we look into the ocean microbiome, we find the same phase diagram, where actually the healthy condition is on the top left corner, and that corresponds to high variance and low value of the exceedance probability distribution function of the power law distribution of the abundance, almost at the tipping point of being an exponential dynamics, very seasonal, versus an healthy condition that is actually power law distributed, with the low exponent and with the higher fluctuation. The question remains about the interorganization of the species collective system. So how do we actually infer the species interaction networks of bacteria considering raw data? Well, this one is actually a very interesting topic, and we tackle this one based on the concept of optimal information network. That is the minimum direct functional or structural network useful for predicting a systemic indicator. In our case, the systemic indicator was the total network entropy associated to the alpha, beta, and gamma diversity of the microbiome. And this work was actually done based on a previous paper published in Science Advances in 2018. The inference of the interdependency is based on the concept of transfer entropy, where time series are used considering time delay and their probability distribution function associated to a certain time delay between species. This transfer entropy is actually calculated only after an entropy reduction approach that considers the conditional entropy as a metric to investigate whether or not the pair of species considered is actually altering the total network entropy that is defined as the sum of the Shannon entropy of each species plus all the potential pairs in the network. Our approach has actually modified the original approach proposed by Villaverde et al. In 2014, and it is certainly more computationally expensive, but it requires to extract the necessary and sufficient information to predict the collective behavior that is really represented by the total network entropy function. So the pattern that we derive for the healthy, transitory, and unhealthy condition are actually network entropy pattern, where network entropy here is actually defined as the sum of the Shannon entropy of each species plus all the transfer entropy pair value, and plus a Gaussian noise that was introduced to actually represent the unexplained variability. What we can see is that the healthy pattern is actually showing a neutral symmetrical pattern where we have equal positive and negative transfer entropy value. Here, actually, transfer entropy that is negative should be considered as misinformation. So certainly transfer entropy is typically is supposed to be only a positive value, but we allowed through the calculation to actually calculate the misinformation part that may or that may not be symmetrical, such as for the transitory and the unhealthy state, where the unhealthy state, as you can see, has a preponderance of positive value. And also what we can see is that there is a shift from the neutral small world or scale-free healthy network to the random network. So environmental variations, such as I said, infection, or for larger scale ecosystem, stormwater or climate change, are the cause of this environmental shift that has a repercussion into the biological organization of system. More generally speaking, in population health, when we deal with large data, we really wanted to do the same thing. And in a paper that came out in 2018 in Science Advances, we actually showed how we can actually select the indicators. In this case, indicators are the nodes that are most relevant to describe a certain population pattern that we care. And there is a certain invariant regime for which whenever we have a variation into the information or network complexity, the total information content does not change. This allows to actually create a novel network visualization in which we focus on the maximum entropy interaction. What is actually interesting is that the distance is actually the minimum of the exponential function considering the mutual information. So those are actually the the strongest interaction between species, and the width of each edge is proportional to the pairwise transfer entropy. Of course, this network can be bidirectional, because transfer entropy can be bidirectional, and the size of the node can be taken proportional to the abundance or the Shannon entropy. In this way, we can actually have a nice interaction network of species. In this case, it's representing fishes, just for convenience as visualization, that can inform about conservation management, because this network is pretty much defining the variation in biodiversity and the likely interaction, at least considering the abundance data that we have. Out of this analysis, what we can find out is that the distribution of alpha diversity as the number of species at each time step is actually following closely the distribution of the microbiome function in terms of total outgoing transfer entropy of a particular node. These distributions are actually very similar to each other, and they are actually quite different with respect to the microbiome structure defined as a pure network analysis, for instance, based on structural degree. So structure is not precisely reflecting function, but rather function is following alpha diversity as an ecosystem services. Just by mapping alpha diversity as the number of species that are diverse over time, we can actually find out a second order phase transition in the human gut, where we have actually the transition from an organized cooperative state in terms of networks to a disorganized cooperation, and in this disorganized cooperation is of course related to much higher variance, as we showed from the Taylor's law. This asymmetry breaking instability is somehow an instability such as a food infection or an inflammation or an immune system malfunction that is somehow disrupting that asymmetrical entropy pattern. And we find the same thing actually in the ocean, where actually there is a striking similarity between the ocean microbiome and the human microbiome. 70% of similarity in terms of species in the healthy state, both in humans and in the ocean. Now, going back to how actually this cooperation is broken, more into the details, what we can see is that if we increase too much the cooperation between bacteria, and their cooperation is actually measured in terms of positive interaction that are changing the abundance of one species in the same direction as the abundance of the other species. So somehow the species are dynamically behaving in the same way. This cooperation is actually detrimental, and that is actually what is happening in the unhealthy state between the most abundant species that are also the least interactive. Now here, positive interaction in a biological sense implies low predictability, because the change in one is always associated to a change in the other. The neutral critical pattern is actually stable, and it has a symmetrical and positive and negative information flow. If you go back to the abundance profile, what we find out is that the most stable species are actually the one that are characterized by a power law distribution with an exponent equal to 1.5. Those are globally stable. The uncommon species in each health state are actually causing the transition. They are the most interactive, and they are actually causing this tipping point. The common species are actually the dominant. The dominant make the norm, characterize, let's say, the average behavior of a particular state, rather than actually producing the spike. And this is somehow reflective of the tragedy of the commons, in a sense, and emphasizing the fact that the hubs, the network hubs, are actually not really very important if we just consider a structure. What we can do in 3D is to map all the potential microbiome states by taking 1 minus the probability distribution of the alpha diversity. We consider the time as a controlling factor, and we define alpha as the complexity variable that informs about the system state. By doing that, we can actually see that if we consider free energy as the total energy of the system minus the entropy, the free energy of the healthy state is monomodal and 1 associated to scale free network, rather than actually the unhealthy state that is actually characterized by multiple modes that are actually locally stable, and they are all associated to different networks. This is somehow reflective what is actually known as the Kareninian effect, that the unhealthy state, or like the unhappy family, as in the romance of Anna Karenina, are actually unhealthy or unhappy for different causes, but the healthy one are actually happy for the same cause. If we consider OT, the outgoing transfer entropy, and as the total metabolic rate, mass specific, that is actually changing the least in the healthy state. And actually we find out that the value of the exponent of this mass specific metabolic rate is actually the one that is matching the measurement in microbial system. Other patterns that are actually quite simple and just based on abundance are related to the average species diversity versus the abundance, that is actually the Preston plot, or the average abundance as a function of species rank. All these patterns reveal the same phase transition without even going into the network complexity issue. Now, if we wanted to measure the importance of each single node, of course, we can do that with respect to all the other nodes, leaving aside the spatial component. So we can do that by actually measuring the information dissipation of one node into the network over time. And we develop a general collective sensitivity indices that are actually related to an information balance equation, where pretty much we have that the total entropy of a network or of an integrated health indicator is actually related to the sum of all the Shannon entropy plus the sum of all the interaction measured by, for instance, the transfer entropy and in noise. Now, calculating that second order interaction index, sigma I, and by calculating as well the singular species importance proportional to the network entropy normalized by the total network entropy, we can actually identify plots that reveal how the healthy condition is actually shaped in terms of species interaction. And we can rank that. And we can use these species, for example, for bioengineering control, such as bacteria inoculation, ecoengineering, in which we actually favor the existence of certain bacteria species by acting on larger species, or geomorphological engineering intervention, if we can actually alter ecosystem structure and have a cascade effect on the bacteria. Of course, these interventions are about ocean system, as you may have thought, but we can do the same thing for the human gut. What we find out is that hubs, or better, they should be called critical nodes, have fewer active interactions, and they are competitive in a sense that they, in terms of predictability, this competition actually lead to higher predictability And the competition is actually a positive thing in a biological sense, because one species can actually control the other. Just considering network hubs based on connection, that is actually not relevant anymore, both for predictability and health. Now, a verification of why outgoing transfer entropy rather than the number of connections is important is that the total network entropy is actually strongly dependent on this function rather than any other function. Then the total information content of a network is really driven by OT rather than geometrical feature or intrinsic node feature. Specific findings to conclude is that the neutral symmetrical pattern corresponds to a healthy state. This corresponds to a small world network state that has a tendency toward the scale-free fractal optimal states. The critical and the neutral states correspond rather than having that criticality is as at a phase transition, unless we consider criticality as a stability function dependent on cooperation. The highest diversity growth rate is the healthiest. And this one is actually representing the maximum feasible entropy across the information landscape. The most abundant are the most beneficial species, but the least interacting in the healthy state. This one corresponds to the highest predictability. And this one is somehow a critical definition of nodes as critical nodes rather than network hubs just based on symmetrical feature or geometrical feature. Final thing is that this Pareto organization can actually be a byproduct of Pareto optimal decisions that are obviously critical for health, such as eating this delicious pasta. And with that, I must acknowledge all my team members, from postdoc to PhD student, funding from University of Minnesota, National Science Foundation, and also Hokkaido University. Thank you very much. If you have any question, feel free to contact me, and I will provide any answer to any question you may have. Thank you.